Mark Farmer, and it's my very great pleasure to welcome you all here this evening to the first of what are 6 lectures titled The Origins Lecture Series. This is a project actually that I've been thinking about and hoping for a number of years, and that is for a group of scientists at the University of Georgia to come out together and tell the public what it is that we do, what it is that excites us, and why it is that what we do, we feel is important both to ourselves and to the community. I'll be joined in this series by 5 of my colleagues representing the major areas of research and science on this campus: physics, astronomy, chemistry, geology, biology. And tonight's lecture is the first in what I hope will be a living example of the motto of the University of Georgia, and that is to teach, to serve, and to inquire into the nature of things. For that is the heart of what we do as scientists. Tonight's speaker is Dr. Magnani of the Department of Physics and Astronomy. He'll be speaking to us on the origin of the universe, which is an area of research for him. He's a radio astronomer using probably the largest telescope on Earth, and that being the Radio Observatory at Arecibo in Puerto Rico. He worked there for a number of years and has continued to do research here at the University of Georgia, authoring over 50 papers on the origins of interstellar gas and how it gives rise to planets, and also co-authoring an introductory textbook on astronomy. So it's my very great pleasure to welcome this evening Dr. Magnani.
Everybody hear me? Yes. Good evening. I'm Magnani. I'm a professor of astronomy here at the university. And tonight I'll be talking to you about the origin of the universe, rather onerous title. In fact, the branch of astrophysics that deals with the universe is called cosmology. And the most important theory in cosmology is the Big Bang theory. So we'll hear a little bit tonight about the Big Bang theory. Now, the Big Bang theory encompasses a lot of things, and it is impossible in 45 minutes, which is my allotted time, for me to cover everything. Okay? So I had to make some choices. I had to skip some things. It's just I tried hard to think about doing everything, but it would have been, in my opinion, it would have been a mess. So I skipped a lot of topics. And what I decided to do is actually cover cosmology, the Big Bang theory, sort of from its inception around 1915 up until developments that take us up until 1985. So now I realize that I'm going to ignore some of the very recent exciting developments that you might have heard about matter and dark energy. I mean, I'll mention them at the end of the talk, but only briefly. And again, it's because they're just, I mean, I know you'd love to sit here for 3 hours and listen to me, but I only have 45 minutes. So without further ado, let's sort of begin. So you want to study the universe, and what do? Well, you go out on a beautiful moonless night, far from city lights, and you see stars. And it's a beautiful, beautiful starscape here, and inspiring and all that. But this is actually not going to tell you very much about the universe, because all the stars that you're seeing are in our Milky Way galaxy. So they're relatively local. Okay, and if you want to study the galaxy, of course, this is what you look at. Well, we want to study the universe. So what we want to do is not study the stars in our galaxy, but study other galaxies. So here's an example of a spiral galaxy. This is our nearest neighbor. It's composed of 100 billion stars, a few hundred billion stars. And as majestic as this object is, okay, you can't see it here with the naked eye. Right? It's just too far away for you to pick it up. So how do we go about studying them? Well, we use telescopes. So what we have here is a stellar field in the constellation Fornax that the Hubble Space Telescope took a close look at. In particular, let's see if my laser pointer works. Okay, in particular, the Hubble Space Telescope looked at this region for a total of over 500 hours. Okay, so that means night after night it would stare at that location, and the images were co-added, and to create a full image. The full moon is put here to give you a sense of how small this region of the sky is. And at least to the level of brightness of these stars, there's no stars in here. There's actually faint stars in there, just so you can see them. But let's see what the Hubble Space Telescope reveals after looking at that region for 500 hours. Okay? The whole image is awash with galaxies. And there are hundreds and hundreds of galaxies. There's only one star in this image, and that's this guy right here. You can tell by the diffraction spikes produced by the telescope. All other objects that you see here are galaxies. Some are relatively nearby, many are just little dots far away. But now you begin to see that if you want to study the universe, you need to know something about galaxies, because they encompass, it's their distribution that will tell you something about the extent of the universe and what it's doing. If you want to find out what the universe is doing, you better find out what galaxies are doing. And in fact, that's what this man did in the late 1920s and 1930s. And indeed, it is the man for whom the Hubble Space Telescope is named after. He's an American astronomer, was an American astronomer. And in the late 1920s, he made a startling discovery. What he discovered was that all galaxies, the ones that we were seeing before in the image, all those galaxies are moving away from our galaxy, from the Milky Way. And the farther away they are, the faster they're moving away from us. Okay? So that was his discovery. It wasn't, he did use revolutionary techniques. One of the techniques he used is effectively the Doppler effect, and it's very similar to the way you get speeding tickets from the police. It wasn't what he had. He was able to do what he was able to do because he had excellent telescopes. There was a revolution in telescopes, and that's why he was able to do this. All right, now normally in science, when somebody makes a staggering discovery, because this was a staggering discovery, normally scientists look around for a theory to sort of put the discovery in perspective, because scientists use the word theory a little bit different than the general public. In science, a theory is a framework for letting you understand and organize your observational or experimental data, for seeing where it fits into the context of your discipline, and for sort of pointing you in the direction of what further avenues to explore. Okay, that's what we mean by theory. Okay? So again, you want to organize your data, you want to see where it fits in the greater scheme of things, and you want to be given directions to continue your exploration. So you might think that at this point, the astronomers have all started scratching their heads trying to come up with this theory to explain Hubble's great observational discovery, but they didn't have to do that. There was already a theory that had been devised about 50 years or so before by somebody you probably recognize, Albert Einstein. And he developed this theory of general relativity in 1915. Now, I put the equation, the set of equations that describe the so-called field equations. All they say, I don't want to get into specifics, but basically they say that matter and energy can curve space and time, something, a concept that I'm sure you've heard of many times. So this theory, devised by Einstein around the time of World War I, was basically the new theory of motion. The old ideas of how things move, Newtonian mechanics, devised by Newton, were superseded by this theory. This theory went a little further. It cleared up a problem with the way Mercury was orbiting around the sun that Newtonian mechanics had failed for decades to address. It made the startling prediction that light should bend in the presence of a very massive object, something that was confirmed in 1919. So it became the new theory of motion. Okay? So around that time, maybe a few years later, 1916 and 1917, Einstein and others, to be fair, he wasn't the only one, applied this theory, this theory of general relativity, to the universe. It was a theory of motion, let's see what it had to say about what the universe was doing. And much to everyone's surprise at the time, the theory made the prediction that the universe should be moving. It should be expanding or contracting. So the fabric, the so-called fabric of the universe, the space-time mesh that we've heard so much about, that couldn't be stationary. It had to be in motion. Now, around that time of World War I, everybody in the astrophysics and physics community and anybody else that had ever thought about it, everybody just knew the universe was stationary. It made no sense for you to think about a moving universe, okay? And so Einstein realized this, and so what he did, since this theory predicted that the universe should be in motion, and everybody knew at the time that that couldn't be the case, what he did was he added a term to it. Oops, wrong thing. But he added this term here, see? It's missing here, he just added, and it's called the cosmological constant. And what this term did is effectively it took out the motion of the universe and gave it a stationary universe that everybody around that time felt had to be the case. Okay? So that's pretty much where things stood for, at least as far as Einstein was concerned. And so you can imagine about 15 or so years later when we heard about Hubble's discovery that the galaxies were moving, you can imagine Einstein just going like this and saying, I could have predicted this. I could have predicted this 15 years earlier. But he didn't. Okay? So what he did was he crashed, he got rid of the cosmological constant. He is supposed to have claimed that this was his greatest blunder. Okay, he went to his death in his grave in 1955, having said that this, the introduction of the cosmological constant into the original field equations, was supposed to have been his greatest blunder. Okay? So let's have a little recap then, because I'm kind of setting the stage for something later on. We haven't seen the last of the cosmological constant. Okay, so around 1915, Einstein develops this theory. Around 1917, he puts in the cosmological constant to explain what people thought the universe was doing at the time. A while later, Hubble discovers that the galaxies are moving away from the Milky Way, and the farther they are, the faster they're moving away. Einstein realizes that what's happening is that space-time is expanding and dragging galaxies with it, so that if you think about the way that works, you actually find what's called Hubble's relation. You find that from any galaxy, all other galaxies are moving away from it, and the farther away a galaxy is, the faster it's received. All galaxies see that. It's a consequence of just everything getting dragged by this expansion of space-time. Okay? So this is sort of where things stood. But remember, the function of a successful theory is to point you in the direction of further exploration. Okay? And by the way, the theory was not called the Big Bang Theory at this time. We'll see where that name comes from shortly. So the next person in our story is George Gamow, a Russian-born physicist and cosmologist who had come to the U.S. before World War II. So a little bit after World War II, his graduate student, Ralph Alpert, they basically started thinking about what the expansion of the universe meant, not as far as the present going forward, but what it meant for the past. Right? In other words, if the universe is doing this, right, as time runs forward. Think of making a movie of the universe. So as time runs forward, the universe is expanding. Just run the movie backwards. So in the past, the universe was smaller. If you go further in the past, it was smaller still. And again, we're talking about our part of the universe, the part that we can see. Okay, so it keeps getting smaller the further back you go. So there has to be a time when the visible universe was smaller than an atom, and hence it had to be a beginning. That's one of the implications of the general relativistic theory. But I mean, Gamow wasn't the first one to think about this. Other people had realized this long before. But Gamow thought about, and Alpert, let's not forget a student, okay, Gamow and Alpert thought about the implications of what a smaller universe in the past meant. Okay? So we need to start getting used to sort of diagrams like this, and especially this concept, to sort of make clear what he did. We need to, kind of remember a couple of things about physics. One thing is that if you're looking at the universe with distant objects, okay, you're looking into the past. The further away you look, the further into the past you're looking. And at first this may sound like an alien concept, but it's not that crazy. If you think about the sun, so you go outside and you look at the sun, which you shouldn't do, by the way. You go outside and you look at the sun, and what you're seeing is not the sun as it is now. You're seeing the sun as it was 8 minutes ago. Because that's how long light has taken to travel from the sun to here. Okay, light doesn't go from one place to the other instantaneously. So it takes 8 minutes to cover 150 million kilometers, 23 million miles. And so you're seeing the sun as it was 8 minutes ago. When you look at the planet Saturn, okay, it takes about an hour and 10, 20 minutes to go from Saturn to the Earth. So again, you're not seeing Saturn now, you're seeing Saturn as it was about an hour and some odd minutes ago. Okay. If you remember the beautiful picture of the Andromeda Galaxy that I put up at the beginning, okay, that thing is 2 million light years away from us. That means when you look at the Andromeda Galaxy, you're not seeing it as it is today, you're seeing it as it was 2 million years ago. Okay? So the further an object is from us, cosmologically speaking, the more into the past we're looking. So if you look far, far into the universe, you're looking at the early universe. Okay? So this thing is not to scale. So you can sort of, this is sort of the time when the universe was smaller than an atom. There was this release of energy. We'll talk about that briefly in a couple minutes. And the universe starts expanding. So you see, this is not to scale. This timeline here, you can think of time as starting here and going forward to now. Okay? And this is not a linear scale. These are tiny, tiny fractions of a second. Here the universe is 5 seconds old. Here it's 3 minutes old. We'll sort of see why at least this number is important. Here it's about 400,000 years old. That means it's been 400,000 years since it started expanding. Here it's 100 million years old. And here it's 13.7 billion years old. Okay, that's how old we think the universe is. So the universe expands, and again, if you're here, we're here. All right? As you look into the distant past, like this galaxy might be maybe a billion light years away. So again, you're seeing it not as it is today, but as it was a billion years ago. Okay? And something twice as far is twice as old. And so again, when you look down here, you're looking at the very young universe. This is the first concept that we need to remember. Okay? Another couple of things. As the universe is smaller, right? The universe is all there is, right? So if I've got a certain amount of matter in a volume of the universe, let's pick a cubic meter. So 1 meter by 1 meter by 1 meter. Okay? If you take this, this is not an average cubic meter of the universe. We've got to go out to the depths of space. But if you take one of those average cubic meters, okay, and you take the matter, hydrogen, helium gas that's in there, and you compress that, going into the past, the cubic meter was smaller, so the amount of matter, on average, has got nowhere to go, and so you find that the density of matter was greater in the past. Or if you want to look at it the other way, as the universe expands, the average density dilutes, because the same amount of stuff has to encompass another greater volume. Okay? So the bottom line is, as you go back in time, the density of matter goes up. But that's also true of the energy density. Right? This, your average cubic volume, again, not this one, but your average cubic volume contains some energy, and if you take that energy and pack it into a smaller volume, the energy density goes up. The reason that's important is saying that the energy density goes up is tantamount to saying that the temperature goes up. So that's the thing to remember. As you go back in time, the temperature, the average temperature goes up. Right now, the average temperature in the depths of space is pretty darn cold. Okay? But that was not always the case. In the early universe, it was actually quite hot. And again, Gamow was not the first person to think about these things, or even this, but he was the first one to put all this stuff together. But again, before we get to what he did, I have to remind you of a couple of things. One of these things is that there's 4 states of matter, 3 of which you're very familiar with. Solid, gas, and liquid, we all know what those are. But there's a 4th state, which is when you take a gas and you give it so much energy that you actually start stripping the electrons off the atoms that make up the gas. So if you remember from high school or cartoons on TV or whatever, okay, the structure of an atom, there's a nucleus, with positive and neutral charges, and the electrons in this ugly schematic diagram are these little, green things. So what happens is when they're all together like this, the atom is neutral. There's no charge. The charges cancel out. Okay? But what happens when you give this gas enough energy, you actually strip these electrons off the gas, and now you have a bath of positively charged nuclei and negatively charged electrons. So now you have a gas that is electrically charged. And that gas is called a plasma. Okay, so nothing to do with God, it's just a physical term for a charged gas is plasma. All right, so what does this have to do with anything? Well, plasmas don't transmit light, dense plasmas don't transmit light very well at all. And you know this because, once again, if you look at the sun, which you're not supposed to do, you remind you of that as an astronomer, okay? The sun is not transparent. The sun is a dense blob of plasma. Okay, you can't see through it, right? That's telling you that light from inside the sun is a tough time getting out. In fact, photons, which are particles of light, okay, photons of light take about 1 million years to go from the center of the sun out. They have to literally fight their way through the plasma. They're continuously scattering and bouncing off these charged particles, being absorbed and re-emitted. It's a real mess. So the point is, it's really hard to get through a plasma. Okay? In that sense, a plasma is very similar to a fog. If you think about a heavy fog, what happens in a heavy fog? In a heavy fog, you don't see very far. The fog is opaque, especially after a few meters. Right? It's like there's a wall of white. What's happening is that if there's a tree way back, 100 meters, 100 yards back here in the distance, you don't see it because the light from that tree never reaches you. It's scattered by the fog so that you don't see the tree. If you don't get the light from the tree, you don't see the tree. So in this sense, a plasma works the same way. Okay? If you have a dense plasma, you're not going to see through it the way you can't see through a fog. Right? So it's a second thing you need to remember. Or I don't know if by now it's a second or third thing. But one last thing, and then we'll get to what Grandma did. Okay? That's why you're giving so much to the class. If you have a dense plasma, right, a dense plasma gives off light. Now I'm going to use light in its bonus terms, like electromagnetic radiation. You can think of light as waves. There's different kinds of light. Right? You're familiar, I'm sure, with optical light. There's a color of the rainbow right there. If the light, the electromagnetic radiation is a longer wavelength, it's not called optical light, it's called infrared radiation. But the only thing that's changed is the wavelength is a little bit longer. Okay, if it's a little shorter, it's called ultraviolet. If it's shorter still, X-rays, gamma rays, going the other way, radio waves, microwaves, etc. So these are all forms of light. The only thing that's changing is the wavelength. Okay? So now what happens is plasma, remember, plasma is that dense charged gas. Plasma characteristically gives off most of its light at a certain wavelength depending on its temperature. For instance, if you've got a plasma at 300,000 degrees, most of the light will come out in the ultraviolet. If you've got a plasma at 5,000 degrees, most of the light will come out in the red and orange part of the spectrum. There is light coming out at other frequencies or wavelengths, but let's not worry about that at the moment. Okay? I mean, think of the sun. We just said the sun was a plasma. It has a surface temperature of 6,000 degrees. That would be a little bit to the right of here, so not surprising that the sun gives off mostly yellow light. You know, the sun gives off infrared and ultraviolet, but most of the sun's light comes out in the yellow. So the point is, a plasma will give off most of its light at a certain wavelength depending on its temperature. Okay? So now, we're finally ready to do what George Gamow and Ralph Alpher did altogether. What they realized is, as the universe, as you look further and further back into the universe, and you're looking at the early universe, when the universe is about 400,000 years old, in other words, when time equals 0 to here, 400,000 years have passed, the temperature of the universe at that point is about 3,000 degrees. Okay, what does that mean? That means that the hydrogen and helium, we'll see where they come from in a second, okay? But the hydrogen and helium that make up the universe are not neutral at that point. They're ionized. They make a dense plasma, okay? So this is a barrier. That's what they realize. You cannot see past here. You don't get any light from when the universe was 3 minutes old, because that light never makes its way through the luminous fog, if you will, that is the dense plasma. So your photons, your particles of light, can only come from here or later. Right? And the reason that happens is, remember, the universe, if we run the movie forward, the universe is cooling. Okay, so it's 3,000 degrees here, a little bit later it cools, the plasma, the charged particles recombine with each other, make a neutral gas, and now the universe becomes transparent. It's as if the fog lifts, if you will. Okay, when the plasma becomes neutral, because the temperature is cooling, because the universe is cooling as it expands, okay, it becomes neutral, the universe becomes transparent, and all those photons that were having such a tough time getting through the plasma now spring free at the speed of light, and zip, they get here. So the point, so what Gamow and Alpha realized is when you look back into the absolute depths of the universe, at the time when the universe is relatively young, 400,000 years, you reach a luminous wall of plasma beyond which you cannot get photons. You cannot get light from beyond that wall. They call this the cosmic microwave background radiation. Okay, and it's got to be everywhere. In every single direction you look, you've got to hit this plasma. Right? So you get excited, you go outside, and you see that the universe is between the stars and stuff is black. You don't see any luminous wall. You know, if this thing is at 3,000 degrees, it should be emitting mostly infrared and some red light. You should see a dull red glow everywhere. You don't. The sky is black. So what happened to this plasma? Well, this is where general relativity comes in again. Okay, general relativity says, yes, these photons coming off the plasma here, when the universe becomes transparent and it can spring free, okay, they were then infrared and red photons for the most part. But the expansion of the universe has lengthened their wavelength. This is a general relativistic effect predicted by Einstein's theory. So by the time they reach to us, by the time they reach us, oops, okay, so they were once here, but the expansion of the universe has shifted their frequency, has lengthened their wavelength, so now they should be here. So that's why you don't see this dull red glow, because it's been shifted to the radio part of the spectrum. Okay, the radio astronomers consider all this the radio part of the spectrum. Right? So this was what Gamow and Alpha did, basically. It was Alpha's PhD thesis, actually. So this is exciting, right? Let's go out and look for it. Well, unfortunately, it's about 1950, and you don't have, radio astronomy is not developed enough for you to detect a faint microwave background of radiation. So what happened to their papers, like what happens to a lot of papers that are ahead of their time, they did publish it, okay, but it was ignored and forgotten. All right? But it was a prediction of Einstein's general relativistic theory applied to the universe. So at this point, so we're around 1950 now, this kind of loose history of cosmology. There's a competing theory about what the universe is doing. It was devised by Fred Hoyle, an absolutely brilliant astrophysicist who was a bit of a contrarian. Okay? His rival theory had a name. It was called the steady state theory. And his theory had no beginning. You know, remember, the theory we've been talking about has a beginning, a time when things are infinitely dense and have temperatures infinite, the universe starts expanding from there. So this is the beginning of the universe. In Hoyle's theory, you don't have a beginning. Okay? So there is no increase in temperature as you go backwards, or decrease in temperature as you go forward. All right? So there's no cosmic microwave background radiation. And I wish we had time to go into it, because it's a fascinating theory, but we don't have time to go into it. Okay? But it was a competing theory. Okay? And unlike the general relativistic theory we've been discussing, where the temperature and density are virtually infinite, as I mentioned, the temperature and density didn't change. So it was Hoyle that named our theory the Big Bang theory. In a radio broadcast for the public over the BBC, he somewhat derisively referred to our theory, the one we were talking about, as a type of Big Bang theory because it kind of started out, with a really hot temperature and kind of this decompression. All right? So it was Hoyle that named our theory the Big Bang theory, and he sort of did it somewhat derisively. Right? So throughout the 1950s, these were two very different theories about how the universe developed. In one, our theory, the Big Bang theory, the early universe was very different from the modern universe. In Hoyle's theory, the universe 33 billion years ago looks exactly like it looks now. So here you've got an example of two theories, and you've got to use observation to discriminate between them. So nothing much happened until 1966 when two astronomers, Arnold Penzias and Bob Wilson, working for AT&T Bell Labs, that's right, the phone company, used this incredibly sensitive antenna. In the 1970s and 80s, Bell Labs had some of the best radio astronomy equipment in the world. Actually, they had a radio astronomy team there. Okay, and, even earlier they had it. But their job wasn't to do radio astronomy. They were astronomers, but their job wasn't to do radio astronomy. Their job was to find sources of static in telephone communication. Way back in the day, for you younger people out there, we had these things called landlines. So you picked up the phone, sometimes it would leave a static in the lines, a little hiss, which was annoying. Sometimes it was due to lightning, sometimes it was due to bad connections. And their job was to ferret out all the causes so that they could be eliminated and could have better phone service. Well, they eliminated everything except a persistent source of static that peaked in the microwave part of the spectrum that was characteristic of matter at a temperature of 3 degrees Kelvin. They didn't know it. It's 1966. They didn't know it, but they had discovered the cosmic microwave background radiation. Okay? Some astrophysicists up the road at Princeton, the Bell Labs laboratories in the middle of New Jersey, up the road at Princeton, some astronomers remembered Gamow and Alpher's work and said, hey, you guys have found the cosmic microwave background radiation. You guys have just killed the steady-state theory. Okay? And in fact, they won the Nobel Prize in Physics in 1978. Now, one of the things I've always wondered about is they discovered it, but they didn't know what they had. The guys at Princeton that knew what they had, they didn't get anything. Gamow and Alpher, who predicted the whole thing, didn't get anything either. So I always thought that it was kind of unfair. It is what it is. All right, so let's sort of see where we fit. We've got a theory, now called the Big Bang theory, we can call it that thanks to Fred Hoyle, okay, that basically explains Hubble's discovery about the movement of galaxies. It's interpreted as the expansion of the universe dragging the galaxies along. We've also explained this luminous wall, this fog here, beyond which we cannot see. Okay, the curve of the universe is about 400,000 years old, from the beginning to here is about 400,000 years. And so at this point, it seems we're kind of stuck, because as I said, you don't get any photons, you don't get any light from here, because this light never makes it through. The universe becomes transparent only here. Right? But, thanks to the Big Bang theory, thanks to this general relativistic theory, we know the temperature history of the universe. We may not see things down here, but we know how hot it is here. So at the 3-minute mark, we know what the temperature is. Okay? So what we do, we being astronomers, we go to our physics friends and say, hey, physics friend, what happens in physics when the temperature is about 1 billion degrees? The physics friend says, you get thermonuclear fusion. Okay? Thermonuclear fusion is when you take particles, slam them together. You got to slam them together. That's why you need the high temperature. High temperature means things are moving really quickly. Okay? So you slam them together, and instead of bouncing off each other, they actually merge, they fuse, and create new elements. So here's an example. This is a form of heavy hydrogen. This is a form of hydrogen that's not as heavy as this one, but it's still heavy. Okay, these two slam together at high speed, produced by a high temperature. You get this reaction. You create normal helium. You throw out a neutron. You also throw out some energy. So this is so that's what happens at 9 billion degrees. This is nuclear physics. Okay. So that's what happened in the universe, because we know the temperature. We can't see light from there, but we know the temperature. So what happened was neutrons and protons got together to make a heavy form of hydrogen deuterium. One deuterium atom is called a deuteron. Okay? So you form a deuteron, you take another deuteron formed by these guys, you slam these two together, you make a light form of helium. Slam that together with another deuteron, and you make regular helium. Okay? The point is that from the time the universe was 1 minute old, so 1 minute after the Big Bang, until it was 3 minutes old, that's your window when the temperature is right for you to make elements by thermonuclear fusion. Okay? So you see where this is going. You can now, because you know what the temperature was and how it was changing, you can predict what elements you make. Right? Now, you might say, how is that possible? I mean, you can't see. You're not getting any photons. But this is just nuclear physics. Okay? This is the same exact theory that goes into making the H-bomb. The H-bomb is a thermonuclear fusion device. Okay? So it's not different physics. It's exactly the same physics. And unfortunately, perhaps, the H-bomb works. So the point is, we understand nuclear physics well enough to be confident that if you tell me what the temperature is, I can tell you what elements you make. All right? Now, this is an ugly graph. I tried to find some nicer graphs, so bear with me a second. So the theory says that if you tell me what the ratio of protons to photons is, matter to light, all right? So you can observe that. You can go out in the universe and say, how much light is there, how many protons are there, what's the ratio? So that falls between these two red lines. It's sort of this, I don't know, red dashed, red dotted, this stripe. Okay? So that's what's observed. The colored lines, like this one, these colored lines, they're predictions from nuclear theory of what the ratio of that particular element to hydrogen is. So, the ratio of light helium to hydrogen is 10 to the minus, it's 0.0001. Okay, a little bit less than that at this ratio of protons to photons. So the point is, this is the theoretical predictions. Okay? So in other words, this is what I was saying. The nuclear physics lets you predict which light elements you make and how many you make. So now you go out and you look at the universe and you say, how much helium is there? How much light helium? How much heavy hydrogen? How much lithium is there? Okay? Your observations are within the blue box. In all cases, the lines fall within the observed blue boxes. In other words, your prediction of how much of these elements you make matches the observations exactly. So using a Big Bang theory and a little nuclear physics, we just predicted what the universe has to be made of. Okay? Now I know you're saying, hey, I've got carbon and zinc in me and all that stuff. That's not a lot of it. 3/4 of the universe is hydrogen, 1/4 is this form of helium. Everything else makes up less than 1%. So sorry, but you're not made of the normal stuff of the universe. The sun is 3/4 hydrogen and 1/4 helium, roughly 1/4 helium, about 1% of everything else. So the sun reflects the composition of the universe. That makes sense. It's where do you think the sun came from? Okay? So anyways, all right? This is a startling prediction. This was work done by many. This is not associated with one person. Many people contributed to this throughout the 1970s. But now you begin to see why Big Bang theory is taken so seriously. Okay, so I've got a little recap of it here. So these are the successes of the theory. This general relativistic theory, remember, it comes from Einstein. Okay, not some guy off the street. So it predicts that the universe should be expanding. something that is confirmed. It's confirmed by Hubble. Now, Einstein, again, this is a little bit of a cheat because Einstein didn't have the courage to make this prediction. He could have, but the time wasn't right. The world wasn't ready to hear that around World War I. Okay? So, but it does, it explains this, if you will. It puts it in the framework of the modern theory of motion. It pointed the way, you know, it pointed you in the direction of looking for the cosmic wave, microwave background, cosmic microwave background radiation, which garnered Penzias and Wilson the Nobel Prize in 1978, and Mather and Smoot, who refined that, you know, got the Nobel Prize in 2006. It also predicted the abundance of the lightest elements in their isotopes, and Fowler got a portion of Fowler's Nobel Prize in 1983 was for this. Okay. Now, if you're wondering about the other elements, why does it shut down at helium? Remember, the universe is expanding and cooling. You've got this window to make the elements. So you calculate what you make if you run out of time before you make anything heavier than lithium. So if you're wondering where your carbon and zinc comes from, that's manufactured in stars. Because stars at their cores are hot enough for thermonuclear fusion to occur. Okay? Now, this takes us to about, I don't know, the late 80s. No, sorry, the late 70s. The late 70s. Okay? And it seems just wonderful, and, you know, there are problems. Well, these are serious problems around 1980 with what I sort of am calling classical Big Bang theory. I would love to talk about them, but we don't have time. And I'm not doing this because, you know, these are, I want to hide the problems. I'm not hiding them. There they are. So, the other reason, so we don't have another hour to discuss why these are problems, but let me tell you, they were serious problems, each and every one of them. But they were resolved by particle physics. Or at least there's a theory that can be tacked onto Big Bang theory that resolves these problems. And that's called inflationary theory. This is one of the architects of that theory, Alan Guth at MIT. Some people think he should win the Nobel Prize at some point. He wrote a book that's a little bit higher level than this talk, but it's an outstanding book. So if you want to know what the problems are and how they were resolved by his theory, which comes from particle physics, by the way. Okay, you know, the Large Hadron Collider, Higgs boson, that stuff. Okay, I recommend this book. Great. Again, yikes. Okay. So this takes us to the mid-80s. I'm almost finished, so I'm going to keep this over. Right. So by the mid-80s, late 80s, this was kind of modern Big Bang theory. You had the beginning of the universe. You got this period of inflation, which clears up those nasty little problems. You got the creation of the light elements between the first and third minute after the Big Bang. Okay, 400,000 years after the Big Bang, the universe becomes neutral and transparent. So now you can see things finally, the fog lifts, if you will. The universe keeps expanding. You know, you make stars, galaxies, people, satellites. Okay. The time from the beginning to now is about 13.7, 13.8 billion years. But this takes us up to, like I said, the late 80s, maybe 1990. In the last 20 years, there's been two staggering discoveries in cosmology. I'm sure many of you, if not all of you, have heard about them. Okay? One of them is dark matter, and the other one is dark energy. They're not the same thing, totally different. Okay? Dark matter, people have been sniffing around dark matter even back in the 70s. They've been sort of coming up on things that made them scratch their heads. Basically, dark matter is an exotic form of matter. See, what we've been talking about so far is normal matter, the stuff you and I are made of, the dog, the sun. That's normal stuff. Okay? Dark matter cannot be normal. It can't be protons, neutrons, electrons. It has to be a new type of particle that doesn't interact with light. That's the name. All right? So the million-dollar question right now is, what are the elementary particles responsible for this exotic matter? We know that the dark matter is there because we see its gravitational effect. So we detect its mass, but we can't see it. Okay? So people have been sort of, you know, particle physicists have been working for the last 20 years trying to identify this stuff. But this is not a problem for the Big Bang. All you're telling in other words, this fits into the Big Bang Theory seamlessly, because what you're saying is, look, we thought there was this much matter, now there's just 5 times as much. Okay, so Big Bang Theory says, so what, I can handle it. This is a different animal. Okay? The last 20 years have shown that the universe, yes, it is expanding, but under the old classical, modern, whatever you want to call it, Big Bang Theory, that expansion with time should be slowing down. And the reason is straightforward. The universe is littered with galaxies. We've seen evidence of that. Okay? So as the universe expands, the gravitational force, you want to think in Einsteinian terms, the curved space produced by these galaxies, should slow the expansion down. It should act like a brake. Okay? There's not enough normal or exotic matter to completely stop the expansion, but it should be slowing down with time. What astronomers have found is exactly the opposite. Not only is the expansion not slowing down with time, it's picking up speed. So if gravity was slowing it down, you need an anti-gravity to make the expansion accelerate. Anti-gravity is an ugly word in physics. Okay? So for many years, when people started pushing this in the early 90s, we all said, you're crazy, go back and look at your data some more. But 20 years later, even the most skeptical astronomer has to be convinced. And again, I'm going to do something that I hate this when speakers do it, but I don't mind when I do it. So, again, it would take about 20 minutes to fully explain the science behind it. But 3 different experiments. The blue experiment, the green experiment, and the orange experiment. They all converge here. That's where they all meet. And what that tells you is there should be some dark energy. So if there was no dark energy, it should be converging down here. And they tell you there's got to be dark matter. Okay? Another line of reasoning, that one Frohlmutter and Weiss and the other guy, escapes me, they won the Nobel Prize a couple of years ago by studying fluctuations in the temperature structure of that famous microwave background radiation. Again, they come to the same conclusion that dark matter and dark energy must exist. Again, it's the Nobel Prize from 2 years ago. So that stuff is there. And at this point, you might be saying, we got you now, because, if Big Bang Theory predicted that the universe should be expanding, yes, but slowing down, and now you find that it's speeding up, are you going to get out of that? It seems like this is the death knell of the Big Bang Theory. But this is where it gets funny. You can incorporate anti-gravity, this accelerating force, into the Big Bang Theory. Okay, so how can we accommodate it? Okay, a little drama. Put it back. Put back the cosmological constant. You have a mechanism, you have a placeholder for this anti-gravity. Mind you haven't explained where it comes from physically. So, all you have is, it fits, it can be made to fit into the theory by putting back what Einstein discarded 80 years ago. Perhaps his greatest mistake may turn out, or his greatest blunder may turn out to be his greatest find. But be careful, you've got to place, this is a placeholder for where it fits. It's up to the physicists now to explain to us exactly what the physical mechanism producing this is. And unfortunately, we're not very close to that. There's not even a decent theory right now. But people are studying it. Okay? So, I sort of covered the first 70 years of Big Bang Theory, I would hope adequately. I've gone way too fast here, but just to give you a flavor of where it's gone from there. But the bottom line is, I hope I've shown you where Big Bang Theory comes from, why it won over all of astronomers by the 1950s, and how it's still the only theory that incorporates all the observational data. So it incorporates all the data. It's an explanation for it. It shows you where everything fits into the framework of physics. And it's pointing you in the directions of where to continue your study. You cannot ask more than that from a theory. Thank you.